Hi, in this video I'm going to show how to make GANs in Python using the Keras library. GANs are generative adversarial networks, and they, as the name suggests, they are a couple of paired networks that are trained against each other to generate data. In most of the cases, the data is images. One example of this, you can search in YouTube for Han Solo deepfake, and you're gonna see how the pictures of Harrison Ford almost 40 years ago were inserted into a scene from the Solo A Star Wars Story movie, and it looked pretty realistic, and you can get a bunch of examples similar to this one. And the material presented in this video is based on the last part of chapter 8 of the Deep Learning with Python book from Francois Chollet, which is in the references. And here's an image of a GAN network. You have the generator, which is going to generate the image, and the discriminator, which discerns if the image is real or fake. And an analogy that Francois Chollet mentioned in the book was that you can see, for example, the discriminator as an expert in Picasso paintings that determines if the paintings are from Picasso or fake. And then on the other hand, you have the generator, which is a fake artist that wants to make a fake of Picasso paintings. So basically, he's gonna start painting Picasso pictures, and he's gonna give them to the discriminator, and it's gonna determine if they are real or fake, and then that feedback is provided back to the generator. So he's gonna get better at making Picasso pictures. But at the same time, the paintings, the fake paintings are fed to a discriminator along with real paintings from Picasso, and both of them are gonna help the discriminator to get better at determining if the paintings are fake or real. So basically, the GANs are trained at the same time, so the discriminator gets better at discerning if the images are real or fake, and the generator gets better at generating fakes. So let's see how this is made in Python. Okay, the first step is to create the generator. We're going to create the generator network, and then we're going to create the discriminator network, and then we're going to put them together and train them. Okay, I'm going to run this. I like to disable eager execution. Probably might not be necessary here, but for some cases it's necessary. And what that means is that when you have a TensorFlow graph, if it has eager execution enabled, it's going to try to compute the values at the time, but you don't want that. You want the TensorFlow a graph to remain as a graph until you want to really execute it or compile the model, whatever, or do the gradient computation. I think this was necessary for the Python example, but probably not for this one. Okay, this might not be necessary as well. This is just in case you want to clear the backend. Okay, so for the generator, we're going to use the functional API from TensorFlow, Keras. So the input is going to be a vector, and that's one of the impressive things that of GANs, as the author mentions, that the generator network is going to be trained to generate images with an input of features. So there's no image input for the generator. Okay, so we're going to have 32 features, and I guess to make this computational accessible, the images are going to be 32 by 32, very small, with 3 colors, and we're going to train this GAN to generate frogs. Okay, so let's build the network with the functional API. You have the input, and then we have the at the beginning everything is flat, yeah, we have a single dimension in here. The author mentions a few tricks to make the GAN training more effective. One of the things that he mentioned is the sparsity, which is good, usually good for deep learning networks. It is not good for GANs. So he mentions a couple of ways of reducing the sparsity. One of them is using leaky ReLUs instead of ReLUs. And the other is that in convolutional neural networks, usually the comp2D is paired with max pooling, but the max pooling creates sparsity. So to avoid that, he's using strides. with the with some of the layers of the convolution layers. Okay, so we'll start reshaping. You can see this as a decoding process, and that's why you see a convolution to the transpose, which you can also see in other CNN applications in which you have decoding from the inner vectors until the output image. Okay, so we keep reshaping using convolution, leaky, and eventually we get the output, which is going to be the image. And he also recommends using tan H as the activation for the generator. Okay, so we got the model using the input and the output graph, TensorFlow graph. And then we get the summary here. You can see that the input is the feature vector, and we have the dense layer at the beginning, not at the output. It's at the beginning. That's kind of opposite order. And then we start the decoding process until we get into the image as the output. That's the image that is the GAN is gonna generate. Okay, now let's go to the discriminator. Okay, let's just run this. The discriminator is gonna be also a convolutional neural network, which takes as an input the image and the channel. And again, for the same resource sparsity, it's gonna use leaky ReLU, it's gonna use traits in the convolution, and the output is gonna be flattened because we're gonna classify. The discriminator is gonna take image as input, and the output is gonna be a boolean saying if the image is real or fake. Okay, so another strategy that he suggested is that stochasticity, randomness, is good for the network, not only for robustness but also for avoiding to getting it stuck, because he mentioned that this is a dynamic process and that can easily get stuck. And to avoid that, two of the strategies, one of them is using noise that we're going to see later, and the other one is using dropout, a dropout layer. But the dropout is also good for regularization, and usually is placed before the dense layer, a fully connected layer, because what the dropout does is basically randomly, in this case with 40% probability, randomly cut connections. And for a fully connected layer like the classification last layer, you're gonna have a bunch of connections, so you have a bunch of connections to break from. So it's recommended to put it before this, not in the convolution, because the convolution is like a sliding window with few connections, and you can see in the web that there are problems with that. You don't want that. Okay, anyway, now let's compile the discriminator and see how it looks. Okay, probably I didn't run it. Okay, there you go. Okay, so the input is the image and the output is the Boolean classification. Okay, now let's compile it. Let's gonna use a low learning rate, a clip value. This is to avoid gradients that explode, putting a threshold that doesn't go beyond it, and then this is to decrease the learning rate. Okay, yeah, so that's the optimizer. We're gonna have this loss, binary cross entropy. Okay, now let's connect the GAN, and you can see the connection between the generator and discriminator in here. The input is gonna be the vector with the features, and the output of the generator, which is the image, is gonna fit the discriminator, and you have the GAN output. Okay, for the GAN, you don't want to train the discriminator. Okay, so we're gonna train the discriminator and the generator separately. The generator is trained within the GAN, and this sounds confusing but this doesn't affect this model because this is already compiled. So when the discriminator is used within the GAN in here, it's like having a copy of the weights. So no, it might. So the important thing is that they are trained separately. Okay, but this flag doesn't affect this one, although you get a warning and that there's a discrepancy. But this is how it makes it work. He mentions that if you train the discriminator while training the generator, you're gonna get problems. Okay, so anyway, with this, we're gonna use also RMS for the GAN with a low learning rate, again clipping value, decay, the same loss function, and this is gonna be our optimizer. Okay, so let's run it. Okay, now this is to generate to train the GAN. This took me to run this. It took me maybe a couple of hours. I was not able to connect the GPU to Python, although I was able to do so very easily with MATLAB. MATLAB is so much easier to do the installation and stuff. But because of that, I'm running in my CPU, so it took me about 2 hours to run 3,500 iterations, like 1/3 of what he intended to do, and still I got some interesting results. Okay, but in order to understand this, we're gonna first run only one iteration so that you can see how it looks. Okay, so let's go down here. Okay, so let's put start in 0. We can see that the training data, this is the real images, is a batch of a set of 5,000 images of 32 by 32 by 3. Okay, so let's get the input vector with the features. The latent dim is the vector size, and we're using a batch size of 20. And this is using a normal distribution, random normal distribution. We're gonna get the input vector for the generator. Okay, so that's 20 by 32, the features, the batch size. Okay, now we're gonna feed that vector into a predictor, and this is gonna give us an image, a fake image. So that's gonna be a batch of 20 fake images. Good. And now we're gonna get the real images from the X training. Batch size is 20, from 0 to 20, so we're gonna get 20 real images, and then we're gonna concatenate the fake and the real. Okay, and now we have a batch of 40, because we have the fake and real combined, because we're gonna train the discriminator now. Okay, so we concatenate them, but also we have to create the labels, and it's kind of weird because once is assigned for the fake and 0 is assigned for the real. Okay, so now we got the labels, but the labels are 40 values. The first 20 are ones, and the second is 0. But again, stochasticity is good, so we're gonna introduce some randomness into the labels. That's not. I mean, at the beginning, I thought that was gonna create forced labels, but that is not the case, because the labels still have the same value. And you can see here that the ones are still ones and the zeros are still zero, just that they have a small deviation for robustness and making the GAN train better, but it's not like it's putting a false expected value. Okay, the discriminator is a functional model, and we're gonna train it with the combined image and the labels, the true and false labels. So we train the discriminator and we get a loss. And yeah, this goes up and down, but eventually should go down. Okay, now we're gonna train the GAN. So yeah, we're gonna provide another vector, another different input vector using their normal distribution with random values, and we're gonna have yeah. So this is the input, and when we train the GAN, we're gonna train it to make the images all real. So the labels are gonna be 0. The expected misleading target is 0. We want all the images to be real, because the generator has to be trained to generate real images. Okay, so now we pass the output and the input, which is the input tensor with the features. Okay, so we get the loss. Yeah. Okay, now we're gonna, the same thing is done many times, 10,000 times in here. We get the real images from this set, which we're getting the frogs, and we're gonna save the images in here, execute this 10,000 times, and we get a random with normal distribution vector with the features. We call the predict. The predict is gonna give us the fake image, and then we do the concatenation that we just saw to train the fake and the real images along with the labels, and then we put the noise for robustness, and we train the discriminator. And then we create another random normalized normal distribution feature vector with all real labels, because we want to train the GAN for the generator to generate real images, and we provide it to the GAN here, and then we get the loss function. When we train the GAN, remember we don't train the discriminator; they are trained separately. Okay, so for each given amount of time, I mean for each 100 steps, we're gonna generate the corresponding frog image, and finally we're gonna display the image with this. Okay, you can see here that the loss is very big at the beginning as expected, and it eventually goes down. Okay, I stop it in here. So you can see the progression between something that doesn't look almost like a frog. It didn't get very far, but I will show you how it looks in step 2600. I make it all the way to 3500, but in 2600 I got the most realistic image, and it looked like this. Let me zoom it so maybe you can see a little bit the eyes, and it looks a little bit like a frog. It requires some imagination, but well, with more time and more computational power, you will get the results. Maybe something similar to what you saw in the Han Solo Star Wars movie. Thank you for your attention. Bye.